Well, that's an old one. So he was, yeah, no, now it's 25. I've seen you go off. It's 15. Is that up there? Yeah. Okay. Welcome back, everybody. This is going to be a session on particle acceleration and non-thermal emission of supernova remnants. Notably, this was originally absent from the program, but somebody pointed out to me that this is an integral part of supernova. So here we are, and I didn't know this because this is what I came back in 2005. So we're going to start off with a lightning talk by Emil, thank you. Who's going to be telling us about thermal X-ray emission from the Synchrotron dominated shock and supernova remnant. This is a lightning talk. So
thank you. So hi everyone, my name is Emil. I'm a postdoc at the Untitled Institute in Amsterdam, working with a colleague and Emmanuel Greco, and here we present our recent work where we find evidence for thermal X-ray emission from the Spectral shock in Tycho supernova remnants. So just to give you a very quick context. I did not see what was the error. Perfect. On the topic, so most of the synchrotron emission from young supernova remnants is confined in very bright filaments right behind the blast wave of the remnants, and of course this blast wave is propagating through an ambient medium, and therefore in the same spatial areas than these synchrotron filaments, you should also find faint signature from shocked interstellar medium. In the case of Tycho supernova remnants, solid proof for such a signature have been lacking for a very long time. And here in this work, we try to apply different statistical analysis from what have been done before to try to find evidence for it. And so what we did was to extract spectra in 5 different regions across the remnants. You can see the spectra on the right here with different normalization for display purposes. And basically, when I'm saying that these are synchrotron dominated, you can see that the spectra are very much featureless. You still have a glimpse of emission lines due to ejecta contaminations, but most of the spectra is only continuum, and therefore it's quite hard to fit because you have a lot of degeneracy when you fit models to it. And what we chose to do is to use as main methods to detect these shock ISM components, to use Bayesian inference. So of course, in 5 minutes, I won't be able to give you a full details on Bayesian inference. I'll just say that it's based on the most hated or loved theorem ever, which is the Bayes theorem, of course. And one of the main upside of Bayesian inference is that unlike fitting your models on your spectra, here you rather sample the whole parameter space of your models over your spectra, which allows you to work with much more information. For example, to do model comparisons or to see if you have different likelihood maximum. And Bayesian inference also gives you access to a very useful matrix, which is the Bayesian evidence, which is some kind of average probability over the whole parameter space. And with that, you can do model comparison, and therefore, to detect this shocked ISM, what you're doing is to try a variety of models. Here, for example, we'll have a single non-thermal model, we have single thermal, we have ISM plus non-thermal, we have ejecta plus non-thermal, and you have combination of everything. And you get these very dirty tables here with a bunch of numbers. I don't want you to read everything, but just to tell you values close to 0 as the better models. And here we can find in this specific case that our best model to represent the spectra are basically taking into account 3 components. You have shock, you have non-thermal emission, you have ejecta emission, and you have a third thermal component that we identify as shocked ISM. You have one example in one of the regions here, one of the associated fits, Bayesian fit that you can see here. And so I don't know how many times I have left, so I would just put my results right away. I bypassed lots of details about the analysis here. I just give you a quick summary of what we found. So as I was saying in the previous slide, the best model are three components model taking into account the various different components. If this second thermal component we find is truly the shock ISM, then we find that it has in average around the remnant an erection temperature around 1 Kelvin, which is lower than the mean shock temperature by 1 order of magnitude. This is quite low, but maybe not as low as you could expect it from strong shock limits. And we also measure post-shock electron density, so it's ambient electron density, sorry, which are consistent with literature around 0.3 across the remnants. And maybe the most interesting result we find, and that I'm not detailing here at all, is the fact that when we try to test all these models on the data, we find that the presence of shock ISM in the shock spectra is anti-correlated with the need of a cutoff for the non-thermal emissions, so the synchrotron emissions, in order to produce the data accurately. So this is quite interesting because theoretically you need for the synchrotron emission some kind of cutoffs there. So I will just stop here, and if you have any sorry, any question, please ask on the Slack, or maybe I don't know if you have feedback here.
Yeah. We have time for one question.
Yeah.
So let's thank our speaker. Okay.
No, it's not a question, it's a comment.
Yeah.
Bayesian evidence works well if your model, if your data is a representation of your model. In astrophysics, it's almost never the case because, as Raf said, if the models that crash. Whereas the better,
I agree.
I mean, so you should be very careful with Bayesian evidence because ultimately, like, no, it will probably lead you astray, especially models with more components will have a lower evidence. The better way of doing this in our land is to do posterior predictive. Have you done that?
I don't think so, but what we are doing is actually to use also other metrics to confirm the same trend, such as, for example, the Bayesian information criterion or the IK information criterion.
But I guess they also still rely on the fact that your data is strong. And so, like, I would use a posterior predictive. How well does your model predict
Yes.
data?
And this is actually not really possible here because some of these models takes weeks to sample of computation.
But there's ways to accelerate this.
Maybe, well, if you have.
I guess this is an offline.
Absolutely. We could go
But
to
I
that
agree with
rabbit
you.
hole.
I agree with you actually, but we are strongly limited by computational issues.
Let's thank our speaker again. Our next talk is, I believe it's virtual, it must be.
Yes.
It's Ryosuke Kobashi. It's a lightning talk. It is again related to Tycho. And it is a CSM model explaining observations of the shock of Tycho supernova. And Ryosuke is from Kyoto. Can you hear us?
Yes.
She's working.
Okay.
So feel free to start. This is 5 minutes.
Okay. This is Ryosuke Kobashi at Kyoto University, and now I will give a talk on Tycho supernova remnants from simulation. Recent work on Tycho Tanaka et al. 2021, we analyzed proper motion and found rapid deceleration in long-term observation using Chandra data in 2003 to 2015. In each position angle, the major shift of the shock and the proper motion is decreased substantially. This is well fit with hydro simulation with the cavity wall structure, and variation over position angle is explained by different age when beginning shock cloud interaction. From Tanaka et al. Data, we also think cavity wall structure as Tycho system, and assuming cavity is uniform, according to Tanaka et al. To produce the data for each region, we parameterize some value of CSM. The parameters are cavity density and cloud properties. Because observation data is angular size and for fitting our simulation to data, distance is necessary. Especially region 8 with position angle around 215 degrees undergoes most substantial deceleration compared to other regions, which in turn means that such region has not yet begun deceleration by interaction with dense regions. Other regions, such as region 1, seem to have already interacted from around 2003. So we assume that there is no information on clouds not yet that 2003 at region 8 is described by uniform cavity, and we use it for estimating this distance. With a certain value of cavity density, we can have 1D hazard simulation results, including fault shock radius, and compare with angular size of region 8. Dividing radius by angular size, we obtain distance to explain conversion between them. This is the region 8 data plots from Untitled. By distance determining, we can fix the value of 2003 and then want to explain other 3 points by cloud properties. This is the region 8. The case of cavity density 10 to the minus 24 gram per cubic centimeters. But depending on cloud position, the meaning of them bendings is different, but every lines here do not explain the slope of first 2003 to 2007 data. Even the case of blue lines 10 to the minus 27 low density not explain the slope of 2003 to 2007 slope. Even much lower density required in inner CSM structure. So here we use uniform wind in a CSM instead of uniform cavity. We can morally explain such slope. Furthermore, by thinking clouds, we can bend these lines and we will be able to explain on remaining 2 points. So from our results, Tycho's data prefer wind wall structure than cavity wall. This is summary. Thank you very much.
Thank you so much for that. Do we have any quick questions? Okay, if anyone has any questions, they can also find him on Slack. So our next talk is by John Raymond here at CFA. It's particle acceleration and radiator shock waves. It's a 15-minute talk.
Thank you. We've been hearing about particle acceleration in very fast shocks, but supernova remnants actually dissipate most of their energy after the shock has slowed down below a couple hundred kilometers per second, which means that the shocks are radiated. The distinction is shown here in the Cygnus loop. If you see those green H-alpha filaments up in the very top, the very faint ones, those are non-radiative shocks. The gas goes through the shock. The neutral hydrogen in the gas is excited and makes the H-alpha. It's a couple million degrees and very low density. So the cooling time, the radiative cooling time, is longer than the age of the supernova remnant, which in this case is 21,000 years. So filaments like that outline the X-ray emission from many, but not all, supernova remnants. And once the speed gets below about 200 kilometers per second, the shock becomes radiative, which means it turns all of the thermal energy of the shocked gas into radiation, which means it's bright. So all of that bright blue oxygen 3 that you see, all of the sulfur 2, and the much brighter H-alpha that go with them are the radiative shocks, which are much slower. But old supernova remnants like this, rather surprisingly, do have substantial radio emission and gamma ray emission. And so we want to understand how you can accelerate the particles in a case like this. Cygnus loop is close by, so we have good spatial resolution. The distance is actually very well known, unlike most galactic supernova remnants. Rob Thiessen found it 725 parsecs, plus or minus 15. And as I mentioned, the age is 21,000 years. So what we want to look at in this radiative shock wave is the development of turbulence in the cooling gas, the cosmic ray acceleration, and the magnetic field amplification. One more. Okay, you can see that little white arrow up there. That shows the region we're going to look at, a very tiny piece of the supernova remnant. And here it is. North is in a different direction now. It's pointing downwards and to the left. But this is what it looks like. And the models for these radiative shocks forever have been simple 1D steady flow models, in which the gas is heated up, it cools down, it makes oxygen 3, which is the blue here, cools some more and makes the red in H alpha plus nitrogen 2 and the green and sulfur 2. So what you expect is that you would see a very neat oxygen 3 filament followed about 1 arc second later by the H alpha and the sulfur 2. And it's obvious that that's not what you're seeing here. One other thing to point out, this is an HST mosaic, and the green area is an HST image from 1997. So you can actually do the proper motion. There it is, it's pretty obvious. You can see the velocity and the variation in velocity as a function of position. 130 kilometers per second is the number I'm going to use. That's the position that we analyzed in most detail. And here is just an example to show you the difference between the oxygen 3 and the H alpha. I mean, it's just clear that those are very different things. It would seem that what's going on is that as the gas cools, turbulence develops, and it kind of rips apart those nice, gentle, sinuous oxygen 3 filaments into the finer scale and kind of spidery structure you see before. In addition to the H alpha and oxygen 3 and other images that we got from HST, we got some ground-based data from Binospec on the MMT. We looked at a series of long slit positions next to each other so that we have the equivalent of an IFU over a piece of this. And I'm not going to go into how we analyze this. There's a lot of complication there, but I'll just kind of give a quick summary. At the top, we have the shock speed. That's from the proper motion plus the known distance. That's known pretty accurately. We have the ram pressure. There's a very clever trick that Don Cox came up with some time ago, in which essentially the geometrical part of that cancels out. So you get rho v squared. We measure that. We know the shock speed and the ram pressure, so we know the pre-shock density, which is 5 per cubic centimeter. We measure the post-shock density from the sulfur-2 line ratio, and that gives us a compression ratio. We know the thermal pressure in the post-shock gas, and that's much less than the ram pressure, only about 1/10. The difference has to be made up by something, and that something is magnetic pressure. So we know the magnetic field in the post-shock gas. And knowing the compression, we now know the pre-shock magnetic field. And one other thing that I'll mention down there, you'll notice vorticity. We have an estimate for that, which is really quite novel. If any of you really care about how fluid dynamics works, you might be interested in that, but I don't really have time to go into that. So there was a paper by Tutu. So when we did this analysis, this was with John Slavin, who is here, Bill Blair, Ravi Sankrit, Igor Chilingarian, and Blakesley Burkhart. We just assumed a simple van der Laan mechanism where you adiabatically compress the pre-existing particles and fields and predict the gamma ray and the radio observation. Tutoni et al. Did a better job. They had 8 years of Fermi data, so they have much better gamma ray data. And what they did was to take templates. They took the X-ray emission, which corresponds to the non-radiative shocks. They took the near UV, which is dominated by hydrogen 2 photon continuum, which looks a lot like H alpha and is a little simpler to use. They took that as a proxy for the radiative shocks. And so if you look at the lower two panels on the right, those just show the gamma ray emission with the X-ray and UV templates superposed. And so then you just take the gamma ray and ask how much corresponds to the X-ray, how much corresponds to the UV. Theoretically, what we did was to take the Voyager 1 local cosmic ray electron and protons. So that's, just outside the heliosphere of the sun. So that's what we can then compress by the known compression factor. And the result is that we took the von der Laan mechanism in which you just adiabatically compress the particles and fields. That works if you have a perpendicular shock wave. That is, the particles are very tightly tied to the magnetic field. And you can match the radio and gamma ray emission to within the geometrical uncertainties, which frankly are fairly substantial, like a factor of 2 or 3, something like that. Tuttoni et al. Used the reacceleration picture. They used the Uchida model. There's another very interesting paper by Giesing and Caprioli, also on the reacceleration. That can give you changes in the spectral indices, which is something that we would really like to look for. But what Tuttoni et al. Found is that both the radiative and non-radiative shocks contribute, whereas we had just assumed that it was all the radiative shocks because we didn't really have decent spatial resolution in the Fermi data that was published by Katagiri et al. Tuttoni et al. Also find very good agreement. The reacceleration picture from Uchida is more appropriate to a parallel shock, where the shock is moving along the magnetic field and the particles can diffuse more easily. So in summary, the compression and acceleration of existing energetic particles rather than diffusive shock acceleration from a thermal tool seems to be able to explain the observations. That doesn't mean that DSA is not happening. It just means that we can explain it without that. We also don't really need any shock amplification, which is perhaps a little surprising given the amount of turbulence that seems to be going on, given the complexity of the H alpha observations. But this agrees with model predictions that the diffusive shock acceleration should be fairly weak at these modest Mach numbers. How can we actually tell the difference between the simple von der Laan picture and the reacceleration? One way would be to get the geometrical factors more accurately. I honestly don't know how to do that. Another possibility is to get accurate spectral shapes in the radio, which seems more feasible to me, and I'm hoping that will be done in the fairly near future. Thank you.
We have some time for questions. Maxine first.
I'm pretty sure at some point radiative shocks will have to become unstable. And that's because if you have a density enhancement instead of puffing up, it cools even better because the collisions and it starts collapsing.
Right.
Now you're saying
So,
this is not the regime we're in, or it's not important?
So most of the paper was actually about the development of turbulence behind the shock. And we looked at 4 different instabilities. One is the thermal instability that you mentioned. One is the thin shell instability of Vishniak from a long time ago. One is the possibility that you just have different magnetic fields in the upstream region. So then when you compress that, you have very different magnetic fields, the parallel and perpendicular components. The parallel component is not compressed, the perpendicular component is compressed. So that then when the gas cools and the magnetic field pressure takes over, then you would get clumpiness. There were 4 instabilities. What was the other one, John? Sorry? Yeah, no, it wasn't mortal. Anyway, so we looked at all of those things. Our conclusion was that, oh, no, sorry, it was just the vorticity, because you have these rippled shocks because you're going past density and inhomogeneities. So you get shear flows, and then that develops Kelvin-Helmholtz instabilities. Right. So that we concluded that that was probably the major one. The thermal instabilities don't quite have time enough to develop in this particular case. And the thin shell instability also doesn't, because you're just in the process of forming the thin shell. So anyway, yes, that was the basic thing that we were looking for in these 2 papers that we wrote. And the conclusion is that, somewhat surprisingly, you're not getting a big amplification of the magnetic field from this developing turbulence.
Yaco, I saw you had a question as well.
You know, one of the conclusions is that maybe you don't have a DSA of those weak models Mach numbers. On the other hand, we know from CME shocks that are even more modest that every now and then we will have solar energetic particles.
Right.
Right. So how do you square these?
By waving my hands. There's a big difference in that in the solar wind, there's a population of superthermal particles that can be picked up fairly easily by the DSA. Whereas an estimate that I did on the back of an envelope years ago was that if you try to have a population of superthermal particles in the interstellar medium, it just cools too quickly by ionization and excitation, so that you only have a thermal pool, and therefore it's much more difficult to make the DSA work in the ISM until you get to high shock speeds.
So it would be an injection problem.
Exactly.
Okay. Thanks, John. That was very interesting. Our next talk is online, and I want to apologize because I was the one that put this together, and we're switching back and forth between online and person.
Note for next time.
Yeah. That is Peter Krustek, Astronomical Observatory of Belgrade, Synchrotron emission of supernova remnants in clumpy media. This is a 15-minute talk. And Peter, whenever you are ready, whenever we grant you access to do things.
To enter the screen, sorry. Is this okay?
Yes.
Okay, thanks. Hello, my name is Petar Kostić, and I come from Astronomical Observatory of Belgrade, Serbia. I am a PhD student, and research that I'm going to present is a part of my thesis. My co-authors are Bojan Arbutina, Branislav Vukotić, and Dejan Urošević. We all know that interstellar medium is clumpy and have fractal structure, which is shown both by surveys of interstellar gas distribution and numerical simulations. The size of these structures scales from the tiniest clumps of order of magnitude of 0.1 parsec, all the way to the largest molecular clouds that have approximately tens or even hundreds of parsecs. It doesn't mean that ISM cannot be of uniform density, only that the clumpiness is some sort of usual manifestation of matter. However, the medium around stars is usually strongly affected by the stars themselves, which is known as circumstellar medium, as we know. Again, numerical simulations strongly suggest that even the circumstellar shells are clumped in the way that density contrasts there can go up to 2 or 3 orders of magnitude. Here we see just a few of many representations of clumpy medium in numerical simulations. Next, the surface brightness to diameter relation is empirically observed and theoretically expected dependence between the radio surface brightness of supernova remnants and their diameter, which you can see on these sigma D plots. The studies of these relations usually analyze the slope of the relation as if it could be fitted with a log-log linear function. But for the galactic sample of supernova remnants, this fitting is very challenging task since the scatter of the points is very large. Further on, in this sigma D plot of Milky Way remnants from Vukotic et al. 2019, we see this little bump in the middle of the graph that might be the signature that the evolutionary paths of some supernova remnants are not straight lines, but have one or more jumps during the evolution. Since we have empirical evidence of interactions of remnants with molecular or atomic clouds, we decided to investigate if these interactions could lead to significant jumps in the surface brightness. We did some simulations. We used both simulations and some analytical models, but first to talk about simulations. The simulations were carried out using my own code from 2019, and the clump setup was as written here. Density contrast between clump and interclump medium were from 3 to 300, and volume filling factors of the clumps were 10 and 25%. The resolution of the cubic box edge for the octant simulations was 320 pixels. So what we did here is that we implemented the model of radial synchrotron emission into the code that calculates the emission from the shock and gives the luminosity as an output. How, we will see. First, let's go through the model of emission very briefly. We try to simplify the model as much as possible. So we imply the test particle case in which the energy distribution of electrons and protons is power law. However, we calculated the amplification of the upstream magnetic field using the recipe from Sabadikari et al. 2017. The emissivity is then calculated using the formula from Pakolchik 1970. We had to limit the maximum proton momentum to obtain the proton energy density, and we approximated it based on the Putushkin and Zirakashvili 2003. Then we calculated the emission locally at the shock. Here I will shortly explain the steps for local calculation of emissivity. First, the algorithm detects the shock points, that is cells, using the second derivative of the momentum in direction of velocity. The emissivity is calculated locally in these points using the velocity from simulation as an input and calculating the shock compression. Then the density can be obtained using that compression and pre-shock density at the cell. The biggest problem is the emitting volume because we have to connect the obtained emissivity to its belonging volume in order to calculate luminosity of that particular shock point. We can express the volume as a product of the emitting shell thickness, which is delta R here, and the part of the shock surface that belongs to that particular shock point, which is A. We set the shell thickness to be 1% of the shock radius in that shock point, and the surface A we calculate using the method I derived using the number of the neighboring shock points, which is illustrated here on the right. But for the explanation of this method, we have no time. Based on the results of simulations, we also developed the semi-analytical hydrodynamic model of the supernova remnants, shock evolving in the presence of the clumps. The model is 1D, but it is based on the 3D geometry of the shock clump interactions. Because we are interested in SNRs of diameters larger than 5 to 10 parsecs, we imply the set of Taylor evolution in the model. The basic idea of this model can be explained by looking at the simple sketch at the bottom of this slide. We have two-phase medium, clumps and interclump medium. Here we sketched the shock, which is in cross section with clumps. If we knew the average velocities of the shock traveling through these two media and the fractions of the shock covered by them, we could calculate the luminosity by the same model we used in simulations. Of course, this is not a trivial problem. First, we have to know the impact that clumps have on the SNR expansion and shock velocity. And second, we have to know the coverage of the shock by the clumps. Because unlike simple picture in the sketch, the dense clumps can survive the shock passing and increase their coverage of the shock, as seen on the snapshot of the shock wave simulation. Here we will present shortly the model of the surface of the shock. So as the shock bends around the dense clumps, if the clumps are very dense, they can sink in the volume of an SNR. The lifetime of surviving clumps behind the shock depends on density contrast and their size. The clumps can sink deeper or shallower in the remnants volume before the shock completely runs through them. So we made an analytical model of the shock surface, which, as we see on the right figure here, is in a good agreement with the simulations. And on the left figure, we see illustration of the model and the snapshot of total momentum from the simulations. Finally, we are on the simulation results and the results of semi-analytic model that I talked about. So black lines represent the total or average values regarding the shock. The red and blue lines represent the clump and interclump values. Top panels show velocity and bottom panels show surface brightness. So we see that semi-analytic model that is represented by the lines is in a good agreement with the dots representing the simulation data. Only at the region immediately after the discontinuity, we see an overestimation from the analytical model, but this is due to the reflected energy from clumps that after a while returns to the shock, and we did not model that. Here we show how the clumpy medium affects the sigma d evolutionary paths. At the left panel, we show uniform density case with 4 different densities in a large range. In the middle, 3 cases of the clumpy medium with different radii of discontinuity. And on the third panel, we show this ensemble of 5 cases with random discontinuity radius between 10 and 50 parsecs. The black solid line represents the average sigma d curve, and the black dashed line is the uniform case. We see how even if the sigma d curves of individual SNRs are more steep after the clumpy medium encounter, the average sigma d curve flattens. The steepening of the sigma d slope of individual SNR after the encounter is shown in the right figure, where we see the beta increases after the interaction with clumpy medium, more pronounced for higher density contrasts. So what we see here is the Milky Way sample of the SNRs. We made this normalized contour plots of probability density distributions. As we see on the first image, the average galactic sigma d curve has a flattened part in the region of diameters from approximately 13 to 50 parsecs, accompanied by quite large scatter. On the right, we see 2 models. Left is the uniform case sigma d sample. Right is with inclusion of clumpy medium of random discontinuity radii between 13 and 50 parsecs. The average density jump is 2 to 20 times. This is on the right panel. This is the same effect as shown on previous slide. I will just show on this third picture. So we succeeded in resembling this average sigma d curve from galactic sample. And here I will show the brief summary of what we have done and concluded from this research. We ran the simulations of supernova remnants in Happy Medium with implemented model of emission using on code to get the empirical sigma d curves. We developed the semi-analytic hydrodynamic model for generating large samples for SNR plot, for sigma d plot, actually, in order to compare them to galactic samples. And what we concluded from this is that clumpy medium steepens the sigma d slope of an SNR, but flattens the average slope of sigma d curve of average sigma d curve of the galactic SNR population. Between 13 and 50 parsecs, there might be an emissivity jumping region in sigma d plot due to individual supernova remnants arrivals at clumps or higher density medium. Of course, we cannot, we must say something about sensitivity selection effect that may have a significant role in the slope flattening of the sample. Also, the break in the sigma d relation is also seen for brighter supernova remnants. The thermal conduction and radiative cooling are not part of these simulations. The both effects work on cooling the shock at the clumps, and it is questionable if the emissivity jumps would be as high as we obtained. However, we wanted to see what happens exactly without any complex mechanisms, because otherwise it would be very hard to separate the impact of different mechanisms. Besides that, the emission model is also simplified. So the main goal of this research is to show if the clumpy medium has any effect on sigma d plot, and we show that it has. The more complex models can be done in the future. Thank you for your attention.
Thank you, Peter. That was very interesting. We have time for a few questions. Do we have any questions online?
No questions online.
Okay. So I have a question. You said that you want to include thermal conduction in a future iteration of this. And maybe you said this right at the end, but I didn't catch it. That the thermal conduction will sort of smooth everything out for you. Or what are you anticipating will happen there? And I apologize if you said this already.
Okay, I said that it is not included in these simulations, but as you said, it would probably smooth out the sigma d curve to some extent. If we know, if we want to know to what extent, we should make simulations with thermal conduction, and I would like to do that. So we will probably try to do that in future. This was just a testing testing phase.
Yeah, I understand. Okay, perfect. Thanks again.
Thank you very much.
So we're going to move on to our next talk, which is searching for thermal emission in X-rays around the Crab Nebula using a blind source separation method. This is Adrian Picano from NASA, University of Maryland. And this is a 15-minute talk.
Okay. So hi, and thank you for having me here and presenting this. My name is Adrian Picano, and I'm in a postdoc position at the Goddard Center with Brian Williams. And so I will present you the search for thermal emission in X-rays around the Crab Nebula with the new blind source separation method. I will take the time to explain briefly this blind source separation method. Sorry that I changed here, but it doesn't change here. So I will take the time to explain the mechanism of this method because it will be in another talk tomorrow, so that it will save some time to the presenter. Yes, it appears my slide do not work here.
Well, oh, maybe I think there was one we had two people sharing accidentally.
Okay.
No. This has never happened before. Sorry. we do have a 5-minute slash at the end, so that's okay, but let me try to figure this out. Okay.
Maybe try going to presentation mode first and then sharing that screen. Sometimes the order helps. Sort of automatically detects.
Yeah, but then I can't get to the controls. Hmm. I mean, I don't know why it says screen sharing is paused. I'm gonna but you have animation, so I can't do it as a.
The animations are not really important. I mean, if it doesn't work, it's not a big deal.
Well. Let me check over here. Okay. That did the check. No idea. Again.
Is that by chance a mask or that? Oh, wait, that's not yours computer.
Yeah, no, yeah, it's weird. It has, we haven't
I
had
my
any.
computer if you want to try and it's not.
We'd have to connect it.
Yeah.
Let me just try one more time after restarting this. Every time I do that, it just stops, like, it just stops sharing for some reason. I'm gonna try the PDF.
I can use the PDF. So I have only one animation. So.
Sorry about that, everyone. Okay. Can you post the video on the Slack later?
Yeah. So, okay, so there, so you can imagine here a little video that maybe is posted on Slack later. So the idea was just to present the fact that thanks to spectral imaging instruments like Chandra, we can capture electrons individually at high energies, which give us 3-dimensional data sets, so cubes. And here you can picture it in your mind rotating around to see everything. And it's kind of amazing to see it, like, as you can imagine it, because we are not really used to picture it as a cube. We rather look either at images or at spectra that we obtain by collapsing the cubes. But by doing so, we lose a lot of information and the correlation between the spectral and spatial dimensions. So the problem that we have is how could we disentangle stuff inside of the supernova remnant, for example, or any kind of extended sources, like the thermal emission, the synchrotron emission, the line emissions, everything. Everything is entangled. And the fact that we lose so much information by collapsing the cubes make us lose a lot of information that could help disentangle these things. So this problem is similar to searching the CMB in Planck data. And there was an algorithm that was written for that is named the GMCA, for Generalized Morphological Components Analysis. And the idea of it was to consider the Planck data cube so as a cube, and to separate it into the sum of components that are seen as images multiplied by spectra plus some Gaussian noise. So here we are in X-ray, so the noise is not Gaussian, but the idea remains interesting. And the idea of my PhD thesis was to use it on X-ray data. So it is written like this mathematically. X represents the data cube, A represents the spectra, S represents the images, N is the Gaussian noise. And the solution looks like that if you don't have any type of constraints. But to disentangle this and to find the solution that is correct, you will need some type of constraints. That's where we use the concept of sparsity. A good analogy to understand it is a one-dimensional analogy. So if you try to disentangle, for example, 3 continuous periodic signals that are summed together, you will not do it in the real space. You will look at the Fourier transform so that you will have only 3 coefficients to disentangle. It's easy. Then you go back to the real space and you have your 3 periodic signals easily. The idea of the GMCA is to use something similar in 2 dimensions that are the wavelet transforms, and in particular Tarlet transforms that are really useful in astrophysics. And these transforms give several images out of one, each image showing the details at a certain scale. So instead of only looking at everything in pixels, we look at the details of different scales, which helps the algorithm disentangle whatever you want to find. So we had this solution, and here we can add a term that enforces the morphological diversity, that is the sparsity of the solution you want to find. And thanks to that, we are able to find amazing stuff. This is an application on real data of Cassiopeia A. Around the calcium line emission, it's difficult to see anything with a simple integration because the calcium is kind of faint, and that's in Cassay. With GMCA, we see that we completely remove the synchrotron pollution, and the image is in square root to show that there are very few pollution left. In a paper that I wrote with Fabio Acero, Tyler, that is here, and Laura Lopez, we used it to find a lot of beautiful images in Cassiopeia A for the line emissions, red and blue shifted components, and other interesting results include the application on Perseus, where we were able to find a X-ray counterpart to the H-alpha filaments that are seen, plus some kind of social forms. So there is no paper on these results yet, but there is one that is being written by Fabio Acero, I think. And so this was to present the algorithm, and it was tempting to try to use that to find a very faint component in the crab that is the possible thermal emission, because it has been shown in Temim et al. In 2012 that the pulsar wind shocked the inner ejecta and the dust that have not been rated yet by the reverse shock, and that it is seen in infrared emission thanks to Spitzer. But no X-ray counterpart of it has been found yet. And actually, I think we didn't see any thermal emission in the crab with certainty. So I wanted to try using that kind of algorithm to this data. And I found something, but I must notify that the results are extremely doubtful. So for now, it's still very preliminary, and I will explain why. So there are actually two thermal candidates, things that might be thermal emission in the crab. The first one I found for the first time by looking at the SeaWorld data from Chandra. So SeaWorld decided to search also for thermal emission and specifically the shell of the crab and didn't find anything. But the interesting thing is that he used data sets, the data that was masked in the middle to avoid the over bright nebula. And so I used this data. I had to hugely rebin it to have enough information to find anything. And I found this tiny peak between 0.3 and 0.4 keV. So it's extremely doubtful. So I checked in XSpec, and actually, if we look at in the same region in XSpec, there is some tiny peak. In Maury's observation from Chandra, there is also a tiny peak. In Weisskopf observation, there is a peak that is not exactly tiny, and that is between 0.2 and 0.4. But in XMM, I couldn't find anything in this region. So this is the first thermal candidate. And the second one is using Weisskopf, because I thought it was really weird to have a bigger peak than in the other ones. So I used the PGMCA, that is like the Poisson version of GMCA, on Weisskopf and on XMM data. And in both, I found some kind of peak between 0.2 and 0.4 or 0.1, 0.2 approximately. So kind of similar, and both are mainly around the nebula. For Weisskopf, it's obviously only around the nebula, and it's it looks like some kind of ring. And for XMM, it's more some kind of big bulk, slightly southern to the nebula. When we look in XSpec, it's something that we can see. So in Weisskopf, we knew that we could see it because we had seen it already. But in XMM also, there is something that could be possibly that kind of thing. If we look at the regions, so the very bulk of the bulk brightness of both candidates on speeder images, it doesn't completely correlate with the filaments, but it's nearby. And it's the fact that it's mainly around the nebula for XMM and Weisskopf would make it consistent with the idea of dust or ejecta eaten up by the nebula. So in conclusion, GMCA has proven really powerful to disentangle stuff, very faint. In plenty of examples, I just brought like the two main ones that I use, but there are plenty of examples of its capacity. Regarding the thermal candidates in the crowd, it is doubtful. I think it's promising in a way, at least. It's worth trying to understand a little bit what is happening. The fact that the first one is very localized may explain the fact that we cannot see it with XMM because like the spatial resolution is not really good. The fact that the second one surrounds the nebula is consistent with the idea of the ejecta being eaten up by the nebula. But the huge issue is that both are below 0.5 keV, which makes it a little difficult. Like there are not a lot of papers talking about XMM or Chandra below 0.5, and there might be possible instrumental effects into that. And it's even worse because of the brightness of the crab. Most of the observations I use are made using some kind of weird exotic modes of the satellites of the instruments to avoid the pileup. So there might be some aspects that are not completely trivial to understand. So it's a work in progress. I don't know how interesting you might find it. And that's it.
Do we have any questions? Fred.
I believe your first candidate in the crab is at a point where the X-ray jet terminates next to an optical filament.
Mm.
So there could be something there, but the energy is rather low. I would think interstellar absorption might be a factor in determining how bright that is.
Yeah, it's indeed quite close to the jet, and also regarding the energy, I don't know how consistent it would be that it is that low, but it is the peak is close to 0.37 keV, which could correspond to a silicon line. So I don't know if it makes sense, but I think there are some silicon. There's some silicon in this region, so it's not completely absurd. I mean, sulfur line. Sorry, it's not.
I have a question. Can you go back to the spectrum from Martin Weisskopf's? Yeah,
This
that
one. Yeah.
That's a really funny shape for a line.
Yeah, and actually, this is weird because this kind of peak is present in almost all the observation, more or less obvious, but it's more or less everywhere. So I don't know how, but it's seen similarly in XMM, so that's why it's not completely absurd either.
Okay, so it's if it's seen in XMM, it may rule it out as incremental, is what I'm getting at. So okay. Do we have any more questions? Okay, thank you for your patience when we sorted out the slides. Let's thank our speaker again. Our next talk
It's another value.
is Maxim Ludikoff. He's going to be telling us about a turbulent model for the Crab Nebula. Maxim, this is a 15-minute talk. And I apologize beforehand, I'm going to step out because I need to go and collect lunch for everybody. So.
Oh, sorry. Doing it again. Do you have any? No. Okay. We're gonna have to put this on PDF.
Yes.
Sorry, I don't know why Keynote has this, there's a known bug with Keynote now, and it's some kind of interaction with when people join, and it's weird. And so now it's not broadcasting Keynote slides. Oh, yeah. But you'll have to advance it.
Very good. So, oh no, it's running automatically.
Oh.
I should do full screen. Okay, so a turbulent model of Crab Nebula. This is paper. This was discussed in 2 papers, and 2 of my collaborators are here, Tay and Pat. So,
Sorry. Right. Oh, not those on the keyboard.
okay, good. So What's the problem? The problem that I'm trying to address is the following. First, turbulence is needed to resolve the sigma problem. And say, Carol Caraniti, they were imagining pulsar nebula as being collection of big magnetic loops. And as these big magnetic loops try to expand, the flux conservation tells them, no, you cannot expand. And that was the problem. And the resolution is that instead of having one big loop, you break it into small loops, and then the underlying flow behaves almost as a fluid, not as a magnetized flow. Second is the X-ray morphology is pretty well described by the Canal-Caraniti model, the shocks. So these observations, these are very old simulations by Komisarov and Lubarsky. These are 2D. The 3D actually do not work as well. But still, it's a good argument that they were able to catch an important ingredient. On the other hand, when we're thinking about crab flares, so here is a X-ray spectrum of the crab flares appear sometimes at as high as few hundreds MeV, and it's all nearly monoenergetic spectrum. And most importantly, that's above what is called the synchrotron burn-off limit. Basically, regardless of the magnetic field, synchrotron cannot produce larger than about 100 MeV in its rest frame. And even to produce that 100 MeV, you need acceleration by DC electric field, which is the same as the magnetic field. And that's exceptional. You cannot achieve this in shock acceleration, but you can do it in reconnection, in relativistic reconnection. And another problem is that almost everywhere in high-energy astrophysics, the radio doesn't fit well to the X-ray fits. And in case of the Crab Nebula, we have a radio spectrum which is very steep, 1.6. The corresponding particle spectrum is 1.6, while the spectral is 0.7. And 1.6 is, again, incompatible with the shock acceleration. Shocks typically give larger than 2. So, how then can we combine the good shock models with something that cannot be achieved by shocks? And so our first hope was to look at the crab in the knot. And here is the image of this in the knot. It's kind of a smiley shape with respect to the pulsar. And when we try to model it, only low magnetized, well, everybody knows what sigma is. Only low magnetized models were able to reproduce this smiley shape. So the in the knot is the surface of the shock, and so this is how the pulsar, the overall shock shape, and it's kind of looking up from the trench here, the in the knot. So since we need small sigma, this is not a site of gamma ray flares, because again, gamma ray flares need very high sigma. So the model is that we're trying to, okay, so this is, okay, it used to be dynamic, but it's okay. So what we're looking here is, it's in part of the Crab Nebula, about 10 to the 17 centimeters. So it's very, very close in. The color here is the magnetization. There is equatorial low magnetized zone, probably striped wind. Then at the intermediate distances, magnetization is high, and you see that it's kind of maroon, so it's about 3 here. That's how it's launched. Okay. Then what we have here, red is the termination shock. Then here what's called the Mach belt. You have a very small, what we call a guide field, almost like sigma 0, and that's it is shock acceleration at this termination shock that eventually gives wisps, and in the classical standard picture of pulsar nebula. Then when we go higher up, you start to have some leftover guide field, and the acceleration stops. So here, at the most part, you mostly thermalize your flow. Then, most interestingly, you naturally form high sigma regions. So remember, we started with sigma 3, and here sigma can reach as high as 40, though in this particular picture it's 5, but in some cases it's called they're reached up to 40, and that's what is called the Cranfield effect in space physics, and it's kind of also related to the sigma paradox. So oh yes, and then the inner knot is, so this is the line of sight, and so inner knot appears somewhere here, so that's the more qualitative picture. So the model that we'll try to develop is that there are 2 acceleration mechanisms. One is Fermi shocks here, and another is the reconnection accelerated population. And again, this all happens very deep in. And then what we do is so first we build a fluid model which could be called anti-canal coronity, in a sense that it's all turbulent, small scale turbulent, and then we inject 2 components which are determined by their spectral indexes, gamma mean and the relative intensity. Then we do the radiative cooling, how these 2 components behave as they are advected within the nebula. As a result, we get radially resolved spectra. It's 1D, but it's not a one-zone model. And then we do different Compton processes, self-similar Compton or external Compton. So, and again, qualitatively, here is our torus that produces population 1, and the bulk that produces population 2. And so this is the particle spectrum, and this is the observed radiation spectrum. So this is the injected population 1, and then it cools. So this is soft X-rays, UV. Then it cools, produces breaks, and this is injected population 2, which also cools. And then most of these breaks can be physically justified, not just parameterization. And then we try to fit it all and iteratively. By all, I mean all. See, it used to be dynamic, but now it's okay. It doesn't show all the. Anyway, we were able to fit broadband spectrum of Crab. Broadband meaning over 20 orders of magnitude in energy, from 100 megahertz to TeVs of energies. And we don't have that many parameters. So we have, and again, we have a very broad population 2 reconnection acceleration, and more narrow but a slightly dominant X-ray acceleration. Population 1 and X-rays. And another interesting thing that relates to the recent observations is that, unfortunately, you don't see the slide, but this is the flattest line in the inverse Compton component, and that's inverse Compton on CMB. And in our old feeds, it cuts a little bit down, but and we'll come back to that. And we can reproduce a few interesting observations. For example, we can reproduce radial evolution of spectral index in the infrared. So these are basically we do different cuts. So these are the spectral index at two frequencies. We'll do different cuts, and in solid are different cuts, and in dashed ones is what our model predicts, which is kind of qualitatively very good, though it's 1D model. And then you remember I was saying that the flattest component that we see in the inverse Compton is inverse Compton on CMB. And then recently there was observation by Lasso of PeV emission, almost 2 PeV emission photons. And interestingly enough, this PeV, and it's clearly inverse Compton on CMB, and it turns out to be in a nice spot where you are almost in the Klein-Nishina regime, but not exactly. So you still have a fairly large cross section. And then the energies for the electrons that you need to produce this PeV is almost the same as what you need to produce Fermi flares. And then, so then the number of observed flares do not produce as many electrons as you need, but it's kind of, by a factor about 100. But it's very reasonable that we see only the brightest flares, and there are many more that are less bright. So in this kind of drunk cowboy who is shooting randomly at us, and then we see one flare every month, but there are many more that we don't see. And even some that are shooting at us, they maybe, if they're not bright enough, they will be buried under the overall population. And then there is always what was bothering me a lot over the last years is this what is called Egret Bomb. So it's statistically kind of significant bond between few MEVs. And this is exactly where you expect the flare particles that are slightly cooled to emit. So the freshly injected flare particles emit at 100 MeV, and if they cool by a factor of few, they will start by a factor of 3. They will emit synchrotron at an order of magnitude smaller. So the suggestion is that cooled flare electrons produce this Egret MEV bump. So in some sense, we took extreme position that the flow is completely turbulent. And polarization, the overall polarization in Krab says that there is some large-scale global field. So this is extreme point of view, but still it may reproduce. It reproduces a lot of observations. So MHD turbulence, not just particle diffusion, the fluid turbulence is needed to resolve the sigma paradox. And that leads to a different from the canal-Carnoti underlying flow. 2 acceleration mechanisms, one near the equator that produces UV and X-rays, kind of similar to canal-Carnoti. And the second is reconnection in the bulk, still deep in, but in the bulk. This is produced very broad, from radio to very high energy gammas, can produce particle indexes less than 2, occasionally generates flares, and these electrons, when they're cooled a little bit, produce the PeV photons and the Egret MEV bump. Thank you.
We have time for one quick question. Does anyone have a question in the audience? Go ahead.
So there have been some recent big simulations that say you should have reconnection in the striped wind before the termination shock. Assuming those are correct, what would be the implications on that on your model?
Yes, yeah, this is already kind of incorporated here. You see here it's dark, so it's low sigma. So the assumption is already included here that the reconnection has already occurred and it's a striped equatorial wind. So that, yeah, so.
So what makes the high sigma magnetization at higher latitude?
Oh, okay, so this line dashed maroon, that's the obliquity of the pulsar.
Okay,
So all here you have striped winds,
and then at high obliquity.
and at higher latitudes, it's all single direction.
Okay.
Let's thank our speaker again.
Thanks for the technical difficulties.
Okay, great. So as the last talk before lunch, I'm going to talk about X-ray polarization in young supernova remnants. It fits in perfectly with the discussions we've been having so far about particle acceleration in these types of systems. Before going into the supernova remnants, very, very quickly, how does one detect X-ray polarization? It's a simple matter. It's not a simple matter. It's a very difficult matter. It comes from the fact that the photoelectric effect, wherein a photon interacts with an atom and kicks off a photoelectron, leaves a trace of its polarization. The electric vector of the incoming photon is correlated with the direction that the photoelectron goes out. And in this diagram up here, the angle phi shows you the deviation of the track of the photoelectron, and the distribution is described by this function down below, which the notable point is the cosine squared phi function. The distribution of the outgoing photoelectron basically is distributed as cosine squared of phi. So it's predominantly, but not totally, in the forward direction for a population of photoelectrons. So you can use that fact if you can track the electrons that come off of the interaction with an incoming X-ray, and that's how it actually is done in the detector. The other relevant piece of information is that for synchrotron radiation, which is what we're talking about and have heard about in the last hour for accelerated particles and supernova remnants and pulsar wind nebulae, synchrotron radiation is polarized. It's polarized with the magnetic vector aligned with the projection of the magnetic field in the emitting region. And so it provides us with information about the magnetic field where particles are being accelerated. And it can be strong. Pi is the polarization fraction, the fraction of the total radiation that is polarized. That depends upon the spectral index of the underlying particle spectrum. P is in the same usage that Maxime was just using. And for something that has a spectrum as steep as 3, which the X-ray emitting particles might, the polarization degree can go as high as 75%. So X-ray polarization can be a very powerful way of identifying magnetic field structures in the systems we're looking at. I'll skip over this part and just note that this is a diagram over here of a photoelectron track in the Hst mission or telescope obtained from the earliest observations of Cas-A. And so that track is used to reconstruct the direction of the photoelectron and therefore figure out the polarization of the incoming X-ray. So for supernova remnants, as we've been hearing, we can get particle acceleration from diffusive shock acceleration at the shocks. That involves particle scattering off of turbulence in the background plasma, which requires pre-existing or self-generated turbulence that can come from the streaming ions themselves. This efficient acceleration process requires a strong and a turbulent magnetic field. And the maximum energy that you can get out of this process depends upon the scale size of that turbulence. The mean free path of the particles is of a scale similar to their gyro radius. And so if the gyro radius is too large, they can escape the acceleration region. So that's how the maximum energy is regulated in these systems. If the synchrotron mission, well, we know from supernova remnants like Cas-A here that we see in the X-rays, thin filaments of X-ray synchrotron emission, that means we've got relativistic electrons in magnetic fields, and we can get polarization information from that. Not only that, but the fact that these rims are very, very thin tells us that the X-rays are being produced very, very close to the shock region. And so even if we use a telescope like Hst, which does not have the type of angular resolution that we see with Chandra, so in other words, if the image is a little bit blurry, you still know that the X-rays came from really, really close to the shock because the Chandra image tells you that, okay? So when we look at this with Hst, we will get X-ray an image of Cas-A in X-rays. I'll get to that image in a second. And we will know that those X-rays, that the synchrotron X-rays are coming from very, very close to the shock. So it allows us to probe the shock region. The distribution of the magnetic field is something we're very interested in supernova remnants, because there's kind of an odd question that comes about from our knowledge of radio polarization measurements, and that is this. This is mentioned earlier when I think John mentioned this, if you have a shock going into a sort of random magnetic field, it's going to basically compress the component that is parallel to the shock front and not the one perpendicular. So you will tend to have, for a shock moving in this direction, the post-shock region having the field sort of aligned with the shock front. So you would expect in a supernova remnant that you would see polarization, magnetic field polarization that implies a tangential magnetic field. And if you look at old supernova remnants, that's exactly what you see. That's a radio polarization map, and you can see that the vectors, which represent the magnetic field's direction, are wrapped around tangentially, like they've been swept up and compressed. But if you look at young supernova remnants, this is Cas-A in the radio, those magnetic field vectors all are radial, okay? So for some reason in young supernova remnants, we see a different formation of the magnetic fields. And part of the question is why? Is it because you have some sorts of instabilities, perhaps Rayleigh-Taylor filaments that are strung along and stretched out, and the magnetic field is carried along in those directions, and the particles are advected and are spiraling along that magnetic field, and that's what's giving you the orientation? Is it because particles are more efficiently accelerated in regions where the shock velocity is parallel to the magnetic field, so that they can spiral along it and not get trapped on the field line around the supernova remnant? It may be any one of those things, and looking at the polarization close to the shock, as we can do with X-rays, is part of the goal. Another part of the goal is recognizing, as I said, that that this process requires a turbulent magnetic field. So we have a couple of things going on. I said that for X-ray, you can get very high polarization fractions from the synchrotron radiation. So maybe we'll see really strong polarization signals. At the same time, we expect the magnetic field to be very turbulent. So on small scales, the directions are going to change all over the place and they're sort of going to cancel out one another. So we're either going to get really strong polarization or we're going to get really weak polarization, and maybe we'll see some of the direction. Hence the experiment. So the left image is a picture of Cassiopeia A in Hst. The color coding blue is higher energies, and so you can see that there are some regions that show higher energies. The reddish stuff is primarily thermal emission, thermal X-rays, which are unpolarized and which are our very complicating background. The figure on the right is a figure that shows what's called the minimum detectable polarization with the observation and apparatus that was used. And so this is, what is it, 42 arc-second pixels on that grid. You can see that in different regions, like in the center where we have a lot of counts, we could detect polarizations down to about 5% or so. In the outer regions, the polarization would be need to be higher in order for us to detect it at the 99% confidence level, which is what that 99 in the NBP minimum detectable polarization stands for. So in looking at PASSE, and this is work that Jakob Vink is led, and this paper is on the archive. I think I put the link down, but on another sheet as well, and the paper was just accepted to publication yesterday, right? Yeah. So anyway, these are figures in a 42 arc second pixel grid showing the polarization degree, how strong in percentage the polarization is in pixels, as well as the significance of the detection. And what you can see is there are not very many significant pixels there, which is perhaps a little depressing. Going to a larger scale, there's not more actually. This tells us a couple things. This is the polarization vector, the electric vector of the photons, which means that the magnetic field will be perpendicular to that. Okay. So this would imply sort of a radial magnetic field. That might be a hint about something. It also says, look, on the scales we're looking at here, the polarization is not strong. So the suggestion would be there's probably a lot of turbulence, which is consistent with what we would expect for conditions for particle acceleration. And maybe the magnetic field is radial, which is sort of what we see in the radio band for young remnants. Okay, but part of the problem here is if you have a lot of turbulent field, or if you have, actually, let's think of it this way. Let's suppose that we had magnetic field or polarization that is actually circularly symmetric. If these are the electric vectors and they correspond to a radial field perpendicular to that, well, if you go around a circular remnant and you try to add them up on a large scale, they're all going to cancel out on you, right? So you can't accumulate a lot of counts. You can't accumulate a lot of counts from the whole remnant without your signal canceling out, unless you play a trick of saying, I'm not going to ask what the directions are relative to one another. I'm going to ask what the directions are relative to a radius. And I'm going to calculate that angle and sum it up. And so that's what we've done. And for the whole remnant, what we find is the plot over here on the right shows us that we get, well, actually, look at the table. The table shows us that for the entire remnant, summing everything up with a model saying, how much do I deviate from a radial magnetic field? We get a 5 sigma significant signal showing us that the angle of the magnetic vector is 90 degrees from a radius. Okay, that means, sorry, the electric vector. That means that the magnetic vector is along a radius, a radial magnetic field with a polarization degree of about 1.8%. When we take into account that there's a bunch of thermal emission there, so that we can ask how much the synchrotron emission is actually polarized, it's 2.5%. So that's what these funny polar plots up here represents. The radial direction gives you the polarization degree. The angle around shows you what the angular orientation of the photons are. So this observation shows us that Cassiopeia A has a radial magnetic field all the way down to the shock region on the small scales that we can probe. And that the polarization fraction is low, implying a very turbulent process. So that's the result for Cas A. We have not stopped there. That was the first observation done with XP, but we've completed an observation of Tycho just recently. You've heard today about these stripes. If you were in the room here last night drinking beer and listening to talks, you heard a short discussion about whether these stripes in here were polarized. We're in the process of doing that experiment right now. Those data are on the ground. We're analyzing them. I'm not going to report any preliminary results about that, but they will be out soon. And finally, we are in the process right now, or is it done? Either we're in the process right now or we just finished looking at SN1006, where we'll be looking at the northeast limb to look for polarization to probe the orientation of the magnetic field along that acceleration region. So the summary is that X-ray polarization allows us potentially to look at the magnetic field structures in acceleration regions very, very close to the shock. Our first observations of Cas A been very successful. We've detected them. We have 2 more supernova remnants on the way. So look for that soon. I'll take any questions if there are. Or we can just have them.
All right, questions?
In Cas A, it seemed that the highest polarized regions were at the edges.
Yes.
So do you imagine that this is the shell that produces high polarization, or it's just observational artifact that in the middle everything cancels out?
No, I don't believe that it is the case. I believe that it is this synchrotron radiation in the outskirts.
The shell.
That's right. And this table of actual results that I kind of went over quickly shows us that if you look at the whole remnant, you get a 5 sigma detection. If you look at the forward shock just by itself, so an annulus just around that outer part, it's about a 4.5 or 4.1 sigma. If you look at just the reverse shock, so inner, but not the dead center, but the reverse shock region, just mixed with a lot of thermal emission, it's about a 3 sigma detection. So I think we see it from all over the place. It's prominent in the outer part because that's where the synchrotron radiation is cleanest.
Get a question from up above.
Oh, yeah. Back in the 90s, Larry Rudnick, Martha Anderson, and I did a bunch of this, like my very first project ever in the radio. And we did a lot of detail work on Cas A. And I know the lot's still done in a sense. How much sort of spatially resolved comparison have you all done? And are your depolarizations
So the depolarization, this is the great thing about doing it in X-rays, is that there is no depolarization with the exception of the spatial depolarization.
Yeah, the spatial depolarization.
Yeah, so
there's no barrier.
that's correct. So the angular resolution of the telescope is about 15-20 arc seconds. So anything on scale smaller than that is going to be confused. The signal to noise makes it more complicated than that. But the overall picture is what I showed before. This image from Cas A on the right is the radio observation. So it's very consistent with that.
Yeah,
But it probes much closer to the shock than the radio does.
right.
Yeah.
So the radio is biased toward where the magnetic field is strong.
Correct. I mean, they both are, but
Even more so, yeah.
Great. Do we have any announcements? Let's thank Pat again, sorry.
Sorry, yeah. I will make one announcement. There are a couple of special events around CFA today that you're welcome to join. We have an ice cream truck down by the tennis courts in the front. And we were extended an invitation for the early career folks here. If you're interested in attending this professional development seminar that's happening in Pratt, you're welcome to attend. And it's essentially the CFA director is going to give a 20-minute talk starting at 1 p.m. And that'll let you get back here in time for our session. And then a little meet and greet also. It's on the random channel of the Slack.
Okay, and we have pizza in the back for anyone who wants it. There's 3 types. There's plain,